The examples we've gone over so far gave us percentages. You knew what the percentages were of the different compounds, or you knew what the mass was. But now what I want to go over with you is how they actually end up getting those numbers. So I've drawn on the board here an example of what are called combustion tubes. And combustion tubes are traps is what they are. And so, for instance, what I'm showing here, this top thing, this kind of, it looks pink to me. I don't know what it looks like to you, but this is what we basically would call a furnace. All right, there would be electric elements in there like you might have on your stove. They heat up, and they're going to take whatever sample you put into this container, and it's going to combust it. It's going to burn. Okay? So let's just say, for argument's sake, that we're dealing with a compound that contains, we know it contains three elements: carbon, hydrogen, and nitrogen. I don't know what X, Y, and Z are. I have no idea. That's what I need to figure out. Okay? So I'm going to burn this material that contains these three elements in this container. Now, what do you need to burn anything? There's three things required to burn something. Number one, you need a fuel. Well, there's our fuel. Number two, you need an ignition source. That's the job of the furnace. It's going to get hot enough to where it will self-ignite, that material, that sample will. The third thing that you need oxygen. So the end of this tube is typically open, and oxygen is allowed, from the air, is allowed to flow in here, and that reaction is going to happen inside of that tube. All right? The combustion gases that are generated, if you think about it, are going to be, there's going to be three of them. From the carbon, when it reacts with the oxygen, I'm going to get CO2. All right? The hydrogen, when it reacts with oxygen, I'm going to get water. And the nitrogen, when it reacts with oxygen, it's going to make a family of compounds called, I'll just call them NOx. It could be NO2, it could be NO3, it could be NO, but it's going to be some oxide of nitrogen. All right? So these gases that are generated during combustion, they make their way into this next tube. And this is what we would call a carbon or a CO2 trap. You will put some, usually they're beads, and there's a series of beads that are in here that have a chemical that will react with CO2 and absorb it. All right, so as this gas kind of makes its way through here and comes into contact with these beads, they're going to pick up any CO2 that runs through here. All right? It then goes into a second container, and this is a water trap. So it will also have a series of beads that are in here. They're stacked in pretty tightly. And the gas is going to come through here. Now, if you think about it, if I had CO2, H2O, and NOx right here, after it goes through this part, what's left? Well, the CO2 has been taken out. What is left is H2O and the NOx. All right, that gas goes into this container, and it makes its way through, going past these different beads, and losing its water. All right? So what comes out of this end? This got the CO2, this got the H2O. What I have left here is the NOx. Now, there is no NOx trap on here because we're not going to need one, you'll see. Okay? But this is the way that this goes. We have a sample that we start with. We're going to trap the CO2 that comes off of that sample here. We're going to trap the H2O that comes off that sample here. And we're going to use the masses of CO2 that was trapped and the masses of water that were trapped to help us figure out what the ratios are between these different elements. All right? So how are we going to know how much was trapped here? This is simple. They weigh this out before they do this combustion, and then they weigh it again when they're done. The difference in those two masses, that's how much CO2 must have gotten trapped. So if you think about this, is the mass of this going to be bigger before or after combustion? It should be larger after combustion because it has the added weight of the CO2 that was generated. This mass of this container should also be larger because it trapped water. Okay? So what I'm going to do is I'm going to kind of reset this a little bit because I need a lot of board space for this one. And we're going to start looking at some masses. So let's say that we have this setup where we've got a sample that we need to figure out what it is. So we basically we know that it has carbon, hydrogen, and nitrogen in it, and we don't know X, Y, and Z. That's what we need to figure out. Okay? So I set this up, and I put 0.1156 grams of the sample in there, and when I burn it, I'm going to get 0.1638 grams of carbon dioxide and 0.1676 grams of water. Now, it may seem to some of you guys that we've violated a big rule in chemistry, and that rule is the conservation of mass. If I burn this, it would seem, if you look at this on its face, that I started off with this much of the sample, but I got way more mass that I captured in here. So hopefully you can explain this, because I can't violate the conservation of mass. I can't. So how is it possible that if I combine these two masses, and I'm not even talking about the nitrogen that came off, that if I combine these three masses, I'm well over what I started with? Well, remember, this isn't pure carbon that you're catching here. This is CO2. This isn't pure hydrogen that you're catching here. It's H2O. And this is NOx, even though we're not going to worry about how much we got of it, at least not right now. So the point here is that extra mass that you seem to see here over what you started with, it came from that O2. That O2 that came in is a lot of the mass that you see here and here. That's kind of problematical for us because we need to figure out what the ratios are between these elements, not with oxygen added. So we're going to have to deal with that, but I'll get to that. So what I need to figure out here right off the bat is not how much CO2 that is here, but how much carbon is contained in that CO2, because that came from the compound. So my first job here is I want to take this mass, so I'm going to say 0.1638 grams of CO2, and I want to end up with just grams of C. That's all I want. Okay, so I need to think about it. Can I go from grams of CO2 to grams of just carbon? Well, if I think about CO2, 1 mole of CO2 has a certain mass. And of that mass, a certain amount of that mass of CO2 is just C. So let's just figure out what those numbers are. If I'm talking about 1 mole of CO2, carbon is 12, oxygen is 16 times 2. That'd be 32 and 12, 44 grams. How many of those 44 grams are carbon? Well, that would just be 12. Really, when you think about what we're doing here, this is simply percent composition, is all this is. I took the mass of the carbon in that compound and then divided it by the total mass. You guys did this already in the percent composition. So if I run those numbers, I'm going to get the number of grams of carbon. This question's like the mother of all empirical formula questions. This will be 0.1638 times 12 and then divided by 44. I get 0.04467. Again, I would caution you guys on a question like this, or any empirical question, I'd caution you about rounding your numbers too early. You're better off leaving a large, even more sig figs than you might be warranted, okay? But fact is, I'll even add another digit. That's a 3 right there. Now I'm going to do the same thing with the water. I have 0.1676 grams of H2O, but I don't want to know how much H2O I have. I want to know how much H that I have, how much hydrogen, because that hydrogen is what came from my sample. So I want to convert this to grams of H alone, hydrogen alone. So I'm going to do the same thing that we did previously, which is I'm going to put grams of H2 on the bottom to get rid of it, and I want to end up with grams of hydrogen. So let's think about 1 mole of H2O. 1 mole of H2O has a mass of 2 plus 16, or 18 grams. So the total mass of 1 mole of H2O is 18. How many of those 18 grams, though, in this compound is actually just hydrogen? Well, there's 2 hydrogens in this, and each one of them has a mass of 1. So I have 2 grams of hydrogen for every 18 grams of water. This will cause our grams of H2O to cancel. Forgot to do that up here. And I can go ahead and do the math on this one. This is 0.1676 times 2, then divided by 18. And I get 0.0186, and then 2 repeating after that. I'll just put 2 of them in. So I have the same number of sig figs that that one does. Okay, so I now know how many grams of carbon that I had in there. I also know how many grams of hydrogen that I have in there. How am I going to figure out the number of grams of nitrogen? I didn't catch that as it came out. Okay, I didn't have a trap for nitrogen. How am I going to figure out how many grams of nitrogen were in that sample? Well, remember, we already said there's only 3 different things in the sample: carbon, hydrogen, and nitrogen. We know how much carbon we had. We know how much hydrogen that we had. How am I going to figure out how much nitrogen was there? Well, if I add this and subtract it from the sample, the original sample, the only thing left is nitrogen. So we're simply going to take our sample, which was 0.1156 grams, and we're going to subtract 0.044673. That's the grams of carbon from that. Okay? So I'll just start doing this. .1156 minus 0.044673, and that gives me 0.070927. Okay, now I've taken out the carbon then. Let's take the hydrogen out. So from this number, I'm going to subtract 0.018622. So I take that number and I'm going to subtract 0.018622. And I get 0.052305. Now, we've deducted the carbon from the original sample. We've then taken that mass that was left over and taken the hydrogen out of it. So what's left at the end here is your nitrogen. So I know that I have 0.052305 grams of nitrogen. Okay? Again, normally I'd be rounding these numbers, but I don't want to get ahead of myself, and then because we're dealing with such small values, a little bit of rounding can do a lot of damage. Okay, at this point, you guys, this question is just like any of those other empirical questions. Remember, we wanted to get into the mass of each of the individual elements, and we're there right now. Okay, I don't have to do any of the assuming I have 100% because I'm not dealing with percentages here. I'm dealing with masses. So what's my next step if I'm trying to get to this ratio between the moles? If I have grams and I need moles, it's time to convert. Grams carbon, moles carbon. I know that for every 1 mole of carbon, I have 12 grams. Here we're looking at hydrogen. I'm going to put grams hydrogen on the bottom so we can get rid of it, and moles on the top. For every 1 mole of hydrogen, I have 1 gram. Again, these numbers here are coming from the periodic table. For every 1 mole of nitrogen, I have 14 grams, okay, of nitrogen. Those are going to cancel, those are going to cancel, and those are going to cancel. So if I take this number that I have here and divide it by 14, I get 0.003736. And then the next digit would be 1. Okay? So that's how many moles. I'm not going to, well, I better because I'm giving a bad example if I don't. I'll write it down below. Moles nitrogen. That's how many moles we have. This is easy. 0.018622. All right? And that's going to be moles of hydrogen. And then this one. 0.044673 divided by 12 gives me 0.0372275. I went further than I had to, but we'll handle the rounding at the end. This is moles carbon. Guys, remember what the next step was? I've converted to moles. The next step is divide by the smallest number of moles. And I can see that it's going to be one of these two. It's going to be this one. 0.00372275. I'm dividing all three of them by the same number. 7.5. Okay. And remember, the purpose for this is I'm making a whole number ratio is what we want. This is making the ratio. This is easy. That's 1. And this one, we're going to... I can tell right away by looking at this, these two numbers, this number is going to be exceptionally close to 1, but I'm going to go ahead and put the numbers in. So this would be 0.0037361 divided by 0.00372275. And I get 1.0036. This is close enough to call 1. All right? This one, we're almost there, I promise. Like I said, this is the mother of all empirical formula questions. 0.18622 divided by 0.00372275. And I get 5.0022. So that is close enough, most definitely, to round to 5. So we have an empirical formula now. Our empirical formula is going to be going to be CH5N. All right, that is our empirical formula here. All right. It also wanted, on this question, they also want to know, well, what's the molecular formula? So remember, to do that, we need to figure out, I'm just going to call it X as my multiplier. It's going to equal my molar mass over my empirical mass, and that's going to give me my multiplier. Well, we were given information here that the molar mass was 31.06 grams. Okay? What's our empirical mass? Well, carbon's 12, and there's one of them, so that's just 12. There's 5 hydrogen, each one is 1, so that's 5. Nitrogen, there's one of them, and it has a mass of 14. So 14 and 12 is 26, plus 5 is 31. So our empirical mass is 31, our molecular mass is 31.06. What's my multiplier? My multiplier is simply going to be 1, which means my molecular formula must be exactly the same, since I'm just going to multiply all of these by 1. It's exactly the same as my empirical. CH5N is my molecular formula. All right? That's it for the mother of all empirical formula questions. It's complicated, but if you look at it, remember I had the same goals as I moved through on this example as I did on the others. I needed to get to grams of the elements that make up the compound. That's where I was right here. All of this over here was simply done to get to that point. Once I got to that point, I was converting to moles, just like the steps told you. All right? Then I divided by the smallest number of moles to get these numbers, which we were fortunate that they were all whole numbers, so we didn't have to multiply all of them by an integer. I might have had to multiply by 2 or multiply all of them by 3. We didn't have to do that. They all came out to whole numbers. And then we found our multiplier using the ratio between the molar mass and the empirical mass, which gave us a multiplier. When we applied that multiplier to the empirical, it gives us the molecular. All right, this is how you do them.